talk about specific goals, talk exam questions. I can circulate and answer multiple questions, whatever you want to do. Whatever. Yep.
2006 number 3. I don't know.
2006 number 3.
Oh, that's the one you have to catch. It's like a fake and I do two other things. Kind of in the middle form.
Oh, two infinites up and infinites with anything.
That one.
Okay.
Yeah, it's three. It's not starting off great.
Okay. University is constructing a large number of new student dormitories, assessed as a plentiful double-type heat exchanger, and each of the dormitory shower drains. Okay. Inner pipe is made of copper, CIDO. Okay, so it's copper pipe with a 5mm thickness wall then. Annular gap is 10 millimeters, okay? So what does that mean? The outer diameter is 35. Wastewater at, okay, certain, okay, so which, goes in the inner pipe, okay, so the hot side is the inner pipe, and so that's wastewater, okay, so that's the hot water. The preheated water comes in the annulus, okay, 38 degrees. So does that have a TH? THO, okay. Fresh water, okay, so you have both inlet temperatures and both mass flows, okay. Fresh water, okay. So what do we want? Heat transfer rate between the two streams.
You need to find the CP.
So you need the CPs for both of them, right?
T-bar.
You need the U between the two, don't you?
Not find Q.
Just to find the Q.
We don't have an outlet temperature, do we?
Yeah, we have the inlet of the hot and the outlet of the hot.
Oh, okay. Oh, THI and THO. Okay,
Yeah.
so just we need CP then.
Yeah.
Yeah. Okay. So CP. So I guess you look up. So TH 30 and 38 and 30. What is that? 68. So 34 Celsius, whatever that turns out to be, and
308. 7.
okay. So okay. So you get the CP for the hot side, and then the cold side you'll just have to estimate CP because you don't know the outlet temperature.
You can calculate it with
No.
No, you need the CP.
You just take it at 18.
I take it at 18.
Okay.
And then equate the Q's. Well, first of all, okay, so A, you get the Q from the hot side, and then the outlet of the fresh water is from balancing the Q's. Okay, so the required length. Okay, so you that.
That's when you use U.
Yeah, that you need a U. So you got to find a U somehow because you got to get an NTU out of it.
Yeah.
Right?
And then your air can be your surface area temperature length.
Yes.
Your number.
Yeah. So the trick then, so that's 27. So that's the bulk of it then is trying to find a U.
Seems pretty straightforward.
So you think it's straightforward?
Seems pretty straightforward.
Okay. Maybe I'll ask the person who suggested it. What's the...
You find the curveball?
Well, it's more of a calculation problem for me. Like I understand the concept of it,
Okay.
just the calculation. They use another type of Reynolds number. So what you have to get.
Well, the inner one is standard, right? The inner one is just a standard inner chapter 8 Reynolds number. The outer one will be a non-circular duct, won't it?
Okay.
It'll be, you have to have a hydraulic diameter for the annulus,
Oh, yes. That's what
Oh, there's the trick.
right? So 4 times the area with the wetted perimeter.
Okay.
I think it turns out to be the DI minus DO, isn't it? Isn't that the hydraulic diameter of an annulus? Or DO minus DI, I mean? DO minus DI?
Those
Yeah, so you have to use the hydraulic diameter, so the other one, otherwise it's exactly the same as chapter 8.
It is. Okay.
There's a table, but the table doesn't make sense.
Okay, so anybody else have an issue with that one?
I find it very
Okay, are we on to the next one?
The Bible.
Who's up? What's the suggestion for the next one?
2011.
So we don't want to go, anything else go over here?
Problem 2. You want to take a look at problem 2?
Problem 2 over here? Okay.
Yeah, that's the one.
Oh, I did one like this.
This is not yours?
That's not mine.
No.
But I did one like that, yeah. Okay. So a pin between two blocks, yeah?
Oh, yeah, you did do one.
Yeah, I did one like this.
Just so they don't know.
Which exam is that?
That's the 2000.
Okay, so what do we want to talk about?
How would you approach like
Okay. Well, first of all, okay, I would say if I see something that looks like that, I'm pretty sure it's a fin, right? It's some kind of a rod with flow over it. Okay.
But does it pin fins? Yeah.
Does it say pin fins? Okay. What a giveaway. Okay, so support, no, so it's a circular, so there's fluid all the way around, so that's easier than the one I did have the insulation on the bottom, right? So you had to arrive with the.
Where's that? What exam?
That's the one that I derivation.
Okay, so what's the other thing? So you see the word two identical devices. What is that telling you? There's symmetry, right? So what are you going to do with the fin? You're going to use the insulated tip version, right? So you would treat this as a fin, and you would say there's symmetry here, so it's insulated right here, so you treat only one side, and it's the insulated tip case of the fin.
Yeah, the one that you did was 2009.
Yeah, and it had these kind of things, right? So you could, so the goal of this.
It was saying that it was generating heat.
Yeah.
It had heat rate at something.
Yeah.
And the other one had another heat rate.
Now these ones have heat rates too? Yeah. So the job of this is to give you the Q on the end.
And then you have to equate it and say that one was transferring energy to the other.
Yeah. Yeah. So if I look at, so I'm going to do half the fin. Okay. So look here. So then I say, okay, what do I know about this end? I don't know TB.
Right.
But I know what the Q is. Right? So you can say the Q here is equal to Q fin, which is the M times whatever, depending on the fin case. So if you pick the case with insulated tip, you look up the quantity. And so you're going to have that K, PA, K, whatever is PA, AC, whatever it is, square root times theta B,
Yeah.
the capital M, and then some other quantity with its hydraulic sign and closest. And, or you can just say that this is TB fin resistance, right? You can say Q here is equal to fin resistance. And that's TB minus T infinity, and you get the fin resistance, either one. But in this case, if you don't have any other quantities involved, like we did other fin ones where you had an insulated wall or whatever else, and then you want to set up a thermal resistance network. But in this case, it's just Q equals Q fin. So you have to do an energy balance on this device to find out what the Q is coming out there, right?
And then when you slice it, like at the, what would be the boundary at L over 2? Like you said, you're using symmetry.
So symmetry is element 2, right here.
So what would be that? What would be the boundary condition right there?
Well, symmetry is zero gradient. Right? Zero gradient means zero heat transfer. Right? So the dt by dx, if this is x, dt by dx is 0. So the temperature profile is going to go like that, right? The minimum in the center, where the gradient is 0.
So if even though the gradient is minimum, do we know the temperature of that location?
You can get it from the fin equation, right? The fin table has the fin temperature distribution, theta over theta b, and it has the fin heat transfer. Those are the two things in that table that you can look up.
And what case would that be?
The insulated tip. Okay, any other? Okay, so where were we going? 2011?
Question 2.
Okay, that's fine. Okay, which one are we going to here?
Question 2.
Okay.
So the question is, how do you know if it's parallel flow or counter flow? Let's say you found all the 4 temperatures, and you're asking us to plot.
Well, you assume counterflow.
Always.
Yeah, you assume counterflow. Unless you're told that it's a parallel flow concentric tube or something like that.
Always assume
Always
counter.
assume counterflow.
That was the question.
Okay. That's easy. And the same thing with the LMTD method, although we didn't do it. If you do the LMTD method, then you got these graphs of correction factors. F correction factors are always based on assuming count. Okay, who gets the next vote? What's the next suggestion?
Well, the whole like unmixed versus mixed thing, that's just based on turbulence and.
Nope, no, the mixed versus unmixed.
Yeah.
If you have, if you have tubes, the tube side is always unmixed. Always unmixed.
Okay.
Because there's in separate tubes. Okay, on a shell side or the other side, outside of the tubes, if it's an open tube bundle, it's mixed.
Oh, right, yes.
If it has baffles or some kind of plates or passages that it goes in between, then that's unmixed.
Okay.
I saw Solomon walking in.
Okay, who's got the next?
That's a good question. He's like,
Nothing?
oh.
Topics then, should we discuss any kind of particular topic? Open. Okay, this is going to be harder than it's not.
So for the fin equation, right? Like when you're saying that derive the fin equation,
Okay.
in your notes you derive the when it's infinitely long, you derive for like when you,
Well, that's in the example.
yeah, in the example, like
In the textbook.
yeah, for the infinitely long case.
Right.
So they're all the same up to like when you get that second order differential equation, and now you have to use the boundary condition, and you have either the convective tip or the insulated tip or
Or the temperature specified.
the temperature specified tip. Like how would you derive like? Because I was
Okay, well, we can look at the solutions that I had to derive if you want. But one, I think a good point to know is when do you choose an infinite fin or not, right? And I think it's 2.65, right, isn't it? ML times L equals 2.65 or higher. So that's an example in the textbook, right? So it can save you some time. I'm not, there's no guarantee you'll use that on this year, but if you calculate that just as a test to see can I use that equation, it simplifies things a lot. Has nothing to do with the derivation, right? It's just for a standard fin. Yes. Okay, so which one was the derivation one then?
2009.
2009? Okay, there it is. Okay. So this one was very similar to the other one, but I just changed it so that the cross-section, okay, so if this had been that cross-section with fluid all around it, would have been your standard fin. You calculate the cross-sectional area and the perimeter and the length and big M and all those things. But so in order to solve this, then you have to, which problem is that for?
Yeah.
Okay, so you've got to take a little dx of the. Okay, so this is exactly the same thing as the fin derivation, right? It's a little dx along the fin, little rod. One dE transfer, and you have conduction in, conduction out, and convection off, whatever the perimeter is. Okay, so that's the only thing. The only thing that distinguishes this from a standard fin equation is the perimeter is not the same as the perimeter. It's not all the way around, right? It's just that top part. So the Q convection, what we would have put for dQ convection would normally be perimeter times dx times h times t minus t infinity. Right? That's what we normally would have put. Okay? And so that's this. Okay, now, I had a few people ask me about this in the last week of classes or whatever, and I know another way to do this is just to leave the perimeter in there. Okay, go to your standard fin derivation. In fact, maybe, I don't know whether I put that as an alternative here. Another way of doing this is take the standard fin derivation and put in W as the perimeter and WT as the cross-sectional area. And then just use that as your fin equation. So that, I don't know, did I put that as the alternative here?
I think you had an alternative solution at the bottom of it.
case did this turn out to be?
It was. We used temperature.
Yeah, that was not, oh, okay.
Just case B, 80 back. So that's where you cut it in half.
Oh, that's what you meant by DT after 0.
Yeah.
This is nutty.
Yeah, that was, no, I don't think that's the same thing. Okay, so let's go back and see what do we get for the actual equation for the fin. Yeah, okay, so the fin equation starts with the HP over KAC, right? Okay, so if we had put in P as W and AC as WT, we would have got 1 over T for perimeter over areas. Okay, so I think another alternative, I didn't put that here, another alternative is to use that equation, or use the original fin equation, and put the perimeter as W and the cross-sectional area as WT. That just gets you the starting point. The rest of it is still, you know, you still have to balance, okay? Like I think one of the issues here was getting the Q from the right-hand side and taking the derivative of the solution. Right, okay. If I remember correctly, okay, so you're sitting here with the fin, and say you now have, okay, what is the goal? The goal is to get the temperature of X function for this. Okay? And then you're applying two boundary conditions. You don't know TV or TL. That's the whole problem with this one. That's what makes this difficult, is you don't know TV or TL.
So you can't use a case.
So you can't use the straight equation as it is, right? Because you don't know TV, you can't use it. So, okay, so there were two ways to do it. One was, well, you take that equation, and then you apply QB. So what do? You say QB is minus K times dt dx at x equals 0. And you say QL is minus K dt dx at x equals L. You put it into the fin equation, and you solve for the fin temperature profile. Okay? Other people, when they solve this, they recognize there's going to be some kind of minimum temperature in between here, and they said, okay, I'm going to take an insulated tip fin up to some spot. So I got a fin going that way, and I have another one, insulated tip fin, going the other way. But you don't know where the X location is, and you got to solve for that. So that was the two things that people did when they tried this problem. But the thing that really got people most of the time was they didn't take the derivative of the temperature profile here. They didn't know what to do with the Q at the end. But anyway, in terms of derivations, the derivation is Q at the left, Q at the right, Q off the top. Use the correct areas, and use the first term of the Taylor series, right? Q of x plus dx is Q of x plus d by dx of Q of x times dx. Right, that's the second term right there. The second term here, right? That's the Q of x plus dx. It's a standard. It's in the it's in the textbook. The textbook kind of thing. So always, what do you get? You always get d by dx of Q of x is equal to minus convection is equal to 0. Well, minus d by dx of that. So that's your second order differential equation. The other thing to recognize in here, another important thing to recognize here, is if you get an equation that looks like this, t minus something on this side, and you got a t here, you can say this is, you can convert this into d2t d theta, right? So anytime, you don't have to leave it in this form if it's causing you problems. You can make this a theta, and you can make that a theta without any changing the equation.
At that location where it's equation 3.64, could you say that the solution to the second order is just like C1 times e to the negative?
Yeah, straight away. Yeah, straight away, yeah. Yeah, as soon as you get here, you know the answer. You know the formula solution.
And would it ever be different? Like, would we have, you won't have convection both coming in, for example, rather than going.
That just changes the sign. Just change the sign here.
Doesn't that change the second order differential equation solution? Would that change the solution?
Well, okay, your coefficient here would be negative, that's all. As far as I know. Well, okay, I don't, in fact, I don't think you'd even worry about that because it all depends on how T infinity compared to T, right? You can have heat added or you can have heat leaving. Yeah, no, the equation wouldn't change. Now, it would change if you had radiation or something like that, but we don't do any of that, just convection.
And uniform cross-section.
Uniform cross-section area.
Would you do varying K varying temperature?
In a fin?
Yeah.
Not the fin, no. In other standard, I've done that in other standard materials, K varying with temperature, yes. But not in a fin, no. No, because then this thing here is a function of temperature too, and this would not be the solution to that differential equation. Okay, so anything here while we're here? Want to talk about anything while we're here? There's unmixed. Or sorry, mixed across the board. When you see, I've said this in class, but I'll say it again because it applies always. When you see, now did I use the word in the problem statement? Yes, okay. So when you see quiescent and you see G in a diagram, what are you going to do?
Free convection.
Free convection, right? It has to be free convection. So you immediately say, somehow here I've got to be able to use a ray number and some kind of free convection equation.
Steady state 1D. Understate.
Yeah. So, okay. And so then it depends on the T minus the T infinity, right? That's your driving force. Whether it's heating or cooling, ray number is always positive. Right? Use the correct delta T, the positive sign.
Got a question. At the end of this question, I guess you ask how.
Right here?
Yeah, decrease. If we are increase or decrease our L, how it changes TS.
Right.
I said that if we increase L, we increase your TS decreases because your H goes up.
Okay.
But the way that I went about it was I put my L into my Rayleigh number, and then I put all that in terms of having an H.
Okay.
And then I just showed that as you increase your L through your Rayleigh number, your H decreases, or your H increases, and then your TS ultimately would decrease.
Was it laminar? Did I say use laminar?
I don't think so.
Okay. Well, the reason I say that is that would be true for laminar.
Okay.
For turbulent, if you have H to the third power, like L cubed, then your H will be constant, independent of L, for the turbulent flow.
Okay. So then, yeah.
It must have been laminar. That's 3.
Yeah.
What's the power? Where's our N equals 1/4.
Yeah.
Yeah, N equals 1/4, so that's laminar. Or yeah.
Yeah, it's just that the way, like in your solution, it was, to me it seemed like it was a little bit of a different approach than the way that I did it. But
Yeah, well, I was just headed for this. This is the key thing here.
Okay.
Because if you had a 1/3 power that was turbulent, then this would drop away. And it would not depend on L.
Okay. Okay.
Yeah, no, that's a bit of a tricky
Yeah, that
concept. Yeah. Okay, so we talked about that one. Okay, so what do you want to do? I mean, I can just take general questions, I can circulate if you probably. The goal here is people, I assume, people have started spending a little time on exams or reviewing the material or saying, I don't understand these key features. So it's a chance for you to ask for clarification of certain concepts or solutions or end of chapter problems, whatever you want. So is it better if I just circulate, or, I mean, still, it's still up to you. Should be something that makes your business worthwhile.
Did you do 8.5 or 8.8 in the next one?
Okay. Are the end of chapter problems, or are they new other ones besides that? Were they on my list or no?
Yeah.
8.5, a fully developed laminar flow through parallel plate channel. Excellent equation has the power. Okay. Okay, I can talk about how you do it, the approach if you want, first. Okay, you guys didn't do that in fluid mechanics then? That's a standard solution.
It looks familiar, but.
Okay, well, the idea. Okay, so you start off, what they've given, okay, so people, I don't know if you got your textbooks here, but 8.5, it gives, it says, for fully developed laminar flow through a parallel plate channel, exponential equation has the form mu d2u dy squared equals a constant, equals dp dx equals a constant. So you reduced your Navier-Stokes equations to 1D steady state, fully developed, so du by dx is equal to 0, v equals 0. So that's what's left over from your u momentum equation. So v equals 0. And then it says show the velocity profile u of y is parabolic and has the form. Okay. And it says u of y equals 3 halves un times 1 minus y squared over u over 2 squared. Okay. Now, how do you get that? You have to set up your okay. You set up a coordinate system, and fluid mechanics textbooks, they either put the coordinate system at the bottom or in the center, right? So is A the half height, or what's the plate spacing?
The plate spacing.
Is the full plate spacing?
Yeah.
Okay, so then let's do it this way. So you have y this way, and x this way, and this is your u in. That's your u in, so square profile coming in. So what do you've got mu d2u by dy squared equals dp dx. Right, that's your, I'll get a better pen than that. Okay, so d2 u by dy squared is equal to 1 over mu dp dx. So du by dy is equal to minus 1 over mu dp dx times y plus c1. So u of y is equal to minus 1 over 2 mu dp dy y squared plus c1y plus c2. It's like solving the 1D conduction equation, right? Solving d2t by dx squared is equal to a constant, right? We had k d2t by dx squared plus q dot equals 0. The same solution. Okay, so you have that. You've got C1 and C2. You've got two boundary conditions. You've got u of 0 is equal to 0, and u of a is equal to 0. So you put that in here, and you solve for the two coefficients, and then you use continuity. Then you say rho times A times UN is equal to integral from 0 to A of U of Y, rho U of Y, dy. And that connects. Okay, so then you get your coefficients. You put your solution from there into here, and that connects your UN with your dp dx. So the solution you get here, the U at A over 2, is equal to 3/2 of UN. So the peak, it's parabolic, and the peak is 3/2 times the velocity of the inlet.
Is that equation for the integral? Is that the continuity, you said?
This is, okay, so the m dot here, m dot in is equal to rho times A times UN, right? And the m dot here is integral from 0 to A of rho times velocity dy. Right? This is U of Y here. So you're saying this area here is equal to this area here. And it connects these coefficients that you got from using those boundary conditions. Okay, so you put those boundary conditions in, what are you going to get? You're going to get C1 and C2 as a function of dpd, okay, that should be dp dx, right? dp dx. dp dx and mu. And you can't connect that to UN unless you do continuity. The same exact thing is done in the textbook for circular 2, right, in chapter 8. Same exact thing is done there. Yeah, the same exact thing is done on page 521 in the textbook for 2. 520 to 522, exactly the same. And they come up with a profile on the top of page 522, which is the U over U mean, is UN.
But the boundary conditions that they use are U at R is equal to 0 and then di U by di R.
Yeah, because in the tube, okay, this is parallel plates. Okay, if you're doing the tube, then your coordinate system, it looks like this, right? You're going from the center to the wall. So if this is R0 or whatever it is, so here it's symmetry, right? Di U by di R equals 0, right there. So it's symmetry here and 0 at the wall. Okay, is that sufficient, or okay? So that was 8.4. What was what was left in 8.5? Or that was 8.5. B part, write an expression for the friction factor using hydraulic diameter. What is hydraulic diameter? Okay, so hydraulic diameter for parallel plate channel is 2 times the plate spacing, right? Did you get that? Okay, it's plate spacing. If you do 4 times the wetted perimeter over, well, okay, I'm sure I did this in class. If you take a duct and you say this is W and this is A, so hydraulic hydraulic diameter, 4 times the area over the wetted perimeter. So it's 4 times W times A over what's the perimeter. So let's take a whole duct. A real duct, W times A, and then the perimeter is what, 2 times W plus A? So that's equal to 2. Now, if I divide the whole thing by W, I get 2A times. So the 2's cancel, so that's 2. And then if I divide by W, I get 1 plus A over W, right? So if I have parallel plates, W goes way, way, way larger, goes to infinity compared to A, right? So this becomes really, really large. So this term drops away and it's twice the plate spacing. That's the hydraulic diameter of parallel plates, is twice the plate spacing. So that's what you would use in a Reynolds number for parallel plates, is you would use, so this equals 2A for A over W goes to 0. So that's the hydraulic diameter. The friction factor times Reynolds based on the hydraulic diameter should be 96 for parallel plates. It's equal to 64 for the circular tube, right? That's in the Moody diagram. Shows the FREs equal, it says friction factor equals 64 for Reynolds for the circular tube, so it should be, I think it's 96 for parallel plates.
They want us to derive that?
Yeah, well, yeah, okay. And how would you derive that? Okay, if it's based on, if you take the definition of this, which is likely tau wall over half rho u n squared, right, friction factor. Okay, so it's tau wall, well, it's either tau wall or dp dx. Okay, if it's dp dx, you have an expression for dp dx, right?
Yeah.
Okay, so then you take the expression for dp dx, you divide by half rho u n squared, and you can collect the rest of the stuff into a Reynolds number, and you'll see friction times Reynolds equals 96. Yeah, and that's what C asked you. The friction factor is estimated from the expression F equals C over Reynolds. C depends on the flow cross section. What is the C for parallel plate channel? It's 96. Or should be. Okay, airflow on a parallel plate channel with separation of 5 millimeters in length. Calculate the mean velocity and Reynolds number. Okay, so the last part, it should be just a calculation. Is the assumption of fully developed flow reasonable for this application? If not, what is the effect on the estimate for U in? Okay, so that I'm not sure about. D part. If you're trying to determine whether fully developed is true or not, then I would use that, the estimate of 0.05 Reynolds. The X fully developed hydraulic is 0.05 O over DH is equal to 0.05 Reynolds. X fully developed hydraulic over DH is equal to 0.05 Reynolds DH. So I don't know whether that's what they're getting at for D, but you could check this and see if it,
I have no idea where it is.
if it's longer than the length of the channel. Is that what they did? I don't know. Should I pull up the solution?
Yeah, you would say that.
Yeah, so are you okay then with the solution? It's the second order differential equation, integrate twice. You get the coefficients from the boundary conditions. It's just like what we did for this, right? When we did conduction, well, the textbook does this one. If you have a source for conduction in a wall, so plain wall, this becomes a parabolic temperature profile, right? T is a function of x squared. But what we did is we did this case, and you integrate twice, you get linear profile. And you can get your two coefficients from the boundary conditions. I did that, yeah. And I even had that on the fall of 12 final exam, the last question.
I think that's what I'm looking at right now.
It should be there. Oops. Yeah, if there's that, and then there's this.
Yeah. This is the one I'm going to ask you.
So that should be the same thing as far as I remember, unless I don't remember it correctly at all.
What, you freaking out? Yeah. And? A good day for M&C too.
Yeah, there. So, starting equation is that. Integrate twice to get that, and then you use your two boundary conditions to get C1 and C2. Solve C1 and C2. Same solutions. It's just that they're messy because it's got convection. And then you substitute values. and you get a temperature profile, 30x plus 85. And then the other thing I got in the corner here is you can verify your solution by doing a thermal resistance network. But now, this part right here is exactly the same thing. But I don't know, I can't say honestly, I don't know what the lat says. Is the assumption of fluid outflow reasonable for this application? If not, what's the effect on? So, I don't know whether you want to pursue that or. I'm assuming there's this kind of a calculation. Now, in terms of what effect would it have on the estimate for U in? So you're making the assumption that you have a fully developed profile where it's not fully developed. Okay, so what would happen? Okay, so when you'd have a profile like this at the beginning, and then you'd have a profile maybe that's like this in the middle, and eventually it's going to come to peak in the center. So if you had estimated this profile with that one, and you're thinking that this is 3/2, you would have overestimating the peak, right? So you've probably overestimated U in. That would be my guess. I don't know for sure. Okay, so that was 8.5. Sorry, the other one was 8.6?
8.8.
8.8? Okay.
Very similar.
Well, okay, I don't know. There is a class of problems where, and I've done this before on final exams or term tests, where you give the equation U of y and T of y, and you ask for the heat flux at the wall or the friction factor or shear at the wall. And what you're asking for is people to know that tau wall is equal to mu di u di y, or mu di u di r, with its radius, mu di u di y, and that the heat flux is minus k dt by dy at y equals at the wall. So you're just using the basic definitions of the tau wall and the heat flux at the wall.
So this one was asking for U and TM, given UI, TY. So you just use.
So you use the integration, yeah. So you use the integration. So you use this. You'd use this. Because you've got the UI profile,
Yeah.
and you just integrate it, and you say that's rho times the height times the U in. So you can get U in from that.
I think I was just confused by finding the, it's in the form of the book, it's AC, the cross-sectional area, but I wasn't sure how to get cross-sectional area for two plates that are.
Yeah, it's just A times, it's just A. It's per unit depth, man. Right, if it's parallel plates, it's all per unit depth.
So for that equation, you'll find the mean temperature, the mean velocity. What about the temperature? How would you find, what equation would you use?
Oh, well, the temperature, okay, so m dot Cp T bulk in would be what? That's the energy in, so it would be integral from 0 to A of rho Cp T dy. Right? This is E dot in. And this is E dot at whatever location you know your T of y. So you can get a bulk temperature from that. If you know the T of y, you can get a bulk temperature from that. So did they ask for that bulk temperature too? Yeah, okay. So same procedure.
Yeah.
Yeah, same procedure. Except this one was with energy, and that one's just mass. Okay? It says, do your UM and TM appear reasonable? I how would you judge that? I guess you'd have to look at the profile and see what the peak is and make sure your mean is less than the peak. It's not going to be algebraically half of the peak, right? Those profiles are, oh, well, the velocity is second order, second power, the temperature is fourth power, so I don't know how you would look at that visually. Okay? I would judge that just by, I mean, if I had all kinds of time, I would plot it. You know, but on a test, I would calculate the peak of it and say, yes, my average is less than the peak, so it seems reasonable. And if it's parallel plates, then the peak would occur at spacing over 2, right? Parallel plates is always symmetric.
Yeah.
Always symmetric.
I think for the question, they actually denote the middle as your 0.
Oh, the middle is 0. Oh, yeah, okay. So the peak is at y equals 0 then. Yeah. Yeah, so the peak is easy then, because the peak on U is 0.75 and the peak on temperature is 5. Okay? Good, it's good exercise of solving this kind of an equation, though. You know, it's what I asked in the last, the other exam. Or solving any really, in this course, I think that's worth emphasizing. In this course, okay, can I delete some of this? In this course, what did we do in terms of solutions like that? We had d2t by dx squared equals 0 and solved, integrate twice for a solution for that. If you had this d2 you do y squared, you integrate twice for that. We had, what else did we have? For the alternative conduction. Oops. What do we have there? So we had q of x times what? Equals integral t1 to t2 k of t dt. Is that right? All right. Negative here? Or, you know, or say 0 to x and 0 to t. So we've done integrations where you do say you integrate this twice, or you have them separated on each side. So what's another one we used? LCM. We had rho v cp dt by dt is equal to what? Q convection, right? Which is minus h times surface area times t minus t infinity. Okay. So we had rho v cp d theta by dt is equal to minus h as theta. So what did we have there? We had 1 over theta d theta by dt is equal to minus h as over rho v cp dt, didn't we? So we did solutions where you integrate twice and solve for coefficients, or we did analyses where you had separated into the two sides and done, put in a function for k there, if k was a function of temperature, or we put in a function of area and determine that, or the LCM we had, we ended up with something like this, and then when you integrate that, you get the natural log on the one side and a constant times temperature on the other side. So you can integrate this one from theta I to theta and 0 to t, right? So there's a number of places where you have, a number of places in the course. So I'm saying this because the number of places in the course you have to be able to do these kind of integrations. If I'm asking you to go back to scratch for some kind of a derivation, okay, there's the Finn equation where you have to do a balance and derive some kind of energy balance and get a differential equation that in the textbook there's a solution. There's the Newton-Raphson problem where you have to do some kind of a collection of algebraic equations into some f of something equals 0. You have to take the derivative of that. So there's some derivatives and integrations required for sure. Now what I've taken to doing on tests is if I'll give you a derivative probably that you might need, right? Or I give you an integral that you need. Like when I did this on the test, I gave you the integral that you needed for that. So I'll either give you an integral or now, if it's a standard derivative that you should know, I will not give it to you. Okay, so there's no guarantee. So what I'm saying is that on occasion I will give you it if I think it's worthwhile, that it maybe is not your standard derivative that you'll remember, I will give it to you, or integral. If it's a standard integral, I will not give it to you. Okay, I'll expect people to know like standard integrals, integral x to the n. You have to know that one.
What is it?
Or derivatives of sines and cos and stuff like that, you should be able to do, right? Even the derivatives of hyperbolic functions, you should be able to do because they're in the textbook.
Oh.
Right? Derivatives of the hyperbolic sine and cos, and they're in the appendix B.
I could do that.
You flip to it?
I could easily look in the textbook.
Okay? What's up next?
Nervous. Oh, yeah. The review session was not
Yep.
good.
Did you do 1E from 2011?
1E. Am I in 2000? No, I'm not in 2011.
Oh.
Okay, yeah, okay. Well, okay, so we talk strategy first? For details? Okay, so
Oh yeah. This is
when you see a statement that something, okay, so maybe okay, so what is it asking for? It says, okay, so at a particular time, so B, so at a particular time it reaches 450 at the surface. At the time in B, the sphere is quickly removed from the bath and covered in perfect insulation with no heat loss. So when you see things like that, wrapped in perfect insulation, or you see something that says average temperature, it's asking for what is the temperature that it will arrive at after a very, very long time. Right? So when it comes out of the bath, there's a T of R distribution. Right? It has a distribution of temperature with respect to radius, right? Whatever it is. So is it heating or cooling?
The center will be hotter than the surface, right?
So it's cooling?
So it'll be heated.
Initially it's 720. Okay. So the center will be hotter, and there's a distribution out to the surface. Okay. So the
But then the surface temperature
Reaches
will rise.
Yeah, they'll reach an equilibrium.
So R. So at that particular time. So this is 0, and this is, say, R0. So whatever it's at what, 450 at the surface, is that right? And whatever the center is, you could determine that, but it's, no, it's going to be the other way around, like that. Right, 0 gradient at the center. And then heat loss at the surface. So that's the temperature distribution at time for B, let's say, whatever the time is. What they're asking for, or what I'm asking for there, is I'm asking for what is this temperature, T bar, such that the area under those curves are the same. So what do? You figure out what is the energy content. Okay, so you have to do the energy calculation. Initial energy is a TI, so M times Cp times
Q
TI. Yeah, Q over Q naught, and you find out what is the energy content here. Okay, and then you know the energy content there. Then you know that the same energy content has to be in the sphere at the end with this T bar. So M times Cp times T bar is the same as, well, it's relative to Ti, isn't it? I think it's relative to Ti. So the M times Cp T bar minus Ti is going to be the same thing as the energy relative to Ti. Or that QO. QO is the energy contained at initial time, isn't it?
Your QO is your ideal energy transfer. Your Q is your actual.
Yeah, but QO is the energy content at the initial state, isn't it?
Yeah.
Yeah. So so you know that it's MCP times Ti, or Ti, or it's relative to T infinity, isn't it? MCP Ti minus T infinity. And then so then you can find the Q here. So then you can find the Q at the same energy content here at that time compared to this energy content. Okay, so was it not clear in the solution that that's what I was doing, or no? Yeah, okay, so the E final is the energy content when it hits Ts equals 450. That's the final of that first phase of calculation. And so between the initial and the final, that's the Q that you get, and that's calculated there already. So then and this is relative to Ti, right? Yeah, relative to Ti. So there's the T bar relative to Ti. So that's the energy content is equal to Q. Now, the sign, I guess, you have to be careful with the sign, because the sign Q is added or removed. Okay, so I don't know. There's various, you see, what else to say? Yeah?
If you were to
I don't know if this helps you know. The way I look at it is it's basically transformed into a lump capacitance because everything has the same. So that's, I don't know.
That's how you viewed it?
Just because, once it's all the same temperature, it might as well be a lump capacitance.
Yeah, that's right, yeah.
So.
Yeah, this part right here, the left-hand side there is like dump capacitance, yeah. And this is just a known, this is just a given.
I don't know what we got there.
Okay,
I don't think I would have just been like, oh, let's see.
what's up now? Should we go through any particular topics? Heat exchangers, everybody's okay with, epsilon NTU? You have to, well, I had a conversation with a couple people in the past, you have to make sure, well, okay, really it's only go one of two ways, right? You're going to calculate either an NTU or epsilon, right? It's a 50-50 thing. So if you're given heat transfer coefficient and a geometry, you're going to get NTU. And then you get epsilon, you'll get Q, and you'll get the stream temperatures. If you're given the Q, like we did before there, that one that we talked about, if you're given the Q, then you can get the epsilon, and you can get the NTU from an equation, then you get the area or the U from that. So just be prepared. Okay, the only hard part about the heat exchanger one then is figuring out what geometry or what condition do I have, what equation do I use for epsilon or NTU. and am I calculating all or part of the overall U, right? Make sure when you do the overall U calculation, or the UA, to get the NTU, make sure you use the total heat transfer surface area of the heat exchanger, the whole area, right? In that example with the annulus, it was easy, it's just the one length, but if you have more than one tube, you have to account for all the tubes, all the surface area of all the tubes. Some people forget that when they do tube banks, for example. And the interior calculation that you do for, say, the H on the inside, that's based on the mass flow in one tube, right? It's not the total mass flow for all tubes. I've had some people do that. They say the mass flow for the tube side is whatever kilograms per second. They put that all in one tube and get a giant, massive Reynolds number and way overestimate the H.
I guess I have a question for the fall 2011 final about the heat exchanger there.
Okay. That's this one. Okay, so which number is it?
It's number 2.
Okay, so do we want to go to the solution, or do you want to go to the problem?
Yeah, we can go to the solution. Okay, so it's asking basically to find the length of your heat exchanger, I guess, of the tube.
Right.
So I understand we find our epsilon, we find our NTU, and then we have our NTU is equal to UA over C min.
Okay.
Okay. So what I did was I went ahead and I calculated my H for the water. We're given the H of the oil, and we're given the K of the tube.
Okay.
So I calculated an R prime total
Okay.
because I don't have the
Don't know
length,
the L.
right?
Yeah.
So then when I had my equation for NTU is equal to L over R total times C min times the number of tubes times the number of passes.
Is it asking for the length per pass?
Yes, it is.
Okay. All right.
So I came up, I ended up with a number of 5.6, but the solution is like 5.75.
Okay. Well, maybe it's just the number of digits carried.
Okay.
What was your NTU?
My
Same as this?
yeah, my NTU is the same.
Okay.
But would that be right? Because I just had my R prime total is equal to, you know.
Yeah. Well, you basically factored L out of all this, right?
Yeah, exactly.
Yeah, that's fine.
Okay. I just wanted to make sure.
Yeah. Make sure you're using the correct diameters here, because they have to have the right areas, whether inner or outer.
Right.
Yeah. No, you can factor an L out of all that.
Okay. I just wanted to make sure. Because if you just scroll down, or actually if you look at the U naught there,
Yeah.
you have 1 over DO over DI times 1 over HI plus DO over 2. I wasn't too sure.
Oh, did I miss a?
No, you times the area out.
Oh, you times the area.
Times out by AO.
Mm-hmm. Do the same thing in our notes.
Did I?
Oh, okay.
Hey, here.
Yeah, okay. That's
But I don't have the correction factor here. Is that missing?
No.
Oh,
yeah.
Yeah.
I think
Yeah.
it's missing
Yeah,
here.
it's missing there.
It's missing there. Yeah, okay, so this is a mistake.
Okay.
It's missing there. But it's recovered here,
Okay.
thankfully.
Okay, so yeah, the only reason why you did that is just to, I guess, get rid of the, or to not really deal with the diameters, I guess?
The L. To get rid of the L.
Okay.
Yeah,
Yeah.
yeah.
Okay. Perfect.
But that's either way, it's fine. You can well, in the end, you've got to factor the L out and calculate it anyway, right?
Right. I guess the difference of 0.1 still had me a little bit nervous.
Oh, well, how was your Reynolds number? Did you get the same Reynolds number?
Yeah. Pretty much everything was the exact same. My H was the same.
3047?
Yep.
Maybe I have,
Yeah, like your answer is 5.75 and mine was 5.6. So I guess it would probably be just my
okay,
calculations.
how'd your area come out? Did you do it separately?
I didn't calculate an area because I just had my NTU is equal to L times the number of tubes times the number of passes over our prime total times C min. If you want to just look at it here, might be easier to see. Just like my NTU is equal to passes times the number of
But
tubes over our total prime times the min.
Okay, but, is there a pi d in there somewhere?
Yeah, it's all in my R.
Oh, it's in your
R
R,
totals.
okay.
Yeah.
Pi d is do, outer? Or inner?
Well, I did it for all of them.
Okay, but if you did it with the, okay, say you did it for outer there. If you did it with inner, would it line up more with this? Like maybe it's just a matter of whether you use inner or outer diameter in the end.
Oh, I see.
Because that would be about the right factor,
Okay, yeah,
wouldn't it?
yeah.
Like I don't know what di and do are, but they're,
Yeah, I think.
if they're 22.3 and 25.4, it's around 1, and then maybe that's enough to, the difference between 5.75 and 5.6.
Right, right. I think that's the areas, the small
So
part.
maybe
there.
use di here.
Okay.
That's a minor thing, okay? I mean, if that happens on a test, it's not gonna, you're not gonna forfeit all the marks of the whole question on something like that, right?
Perfect.
But you gotta remember, I'll put a decent amount of marks if you're asking for passes and tubes and stuff like that. You gotta have the right, you know, if it's per pass or whatever,
Yeah.
you have the right, you know, entities here. For the DO and DI, you know, people make those mistakes.
Yeah, those, okay.
So you ask for a tube length or pass length? Like either
Well,
one would be
okay,
different.
it's either tube length,
Yeah, which you don't
which
multiply
is
with
the
passes.
total for all passes, which
Right.
is fine.
Yeah.
Or you say per pass,
Which
and
is
you just
also-
divide it by number of passes, that's all.
And pass length is also shell length, right?
Could be, yeah, typically, yeah.
1 out of 5. I'm gonna 1 out of 5.
Okay, yeah.
There's how many NTU of a unmixed crossflow, like unmixed,
Devin's here, didn't see him before.
would you typically just use the figure for that? Or would you want us to calculate through on the other equation for it?
Well,
Is, you're giving-
okay, is it one that, you have an equation, it's not the one that has no equivalent, is that right?
It is, like, this equation providing your efficiency, but not for the NTU itself.
Okay, I'm not gonna give you one that you don't have an equation for. So my preference is the equation. I won't mark the value written in the graph wrong. I mean, the wording I'm gonna use is using the correct equation for epsilon or NTU, solve, blah, blah, blah. Okay? So the implication is that you're expected to use the equation. If somebody is sitting there at the end of the test and they say, I want to finish this problem off, but it's faster for me to read the equation, I'll give people some credit for a graph reading if it's correct, but it's not full because I'll expect the equations.
I don't know.
No, I mean, if you get time enough not to do the equation, you want to read a graph just to carry on and finish the problem,
Sorry.
that's fine. It's like if you get stuck making an assumption, right?
Before Saturday.
So I tell people, if you're sitting there saying, I don't know what to do,
It's like, what am I doing?
making a reasonable assumption and write the assumption there and say, this is what I'm gonna do, and then you carry on, right? You don't forfeit the rest of the problem.
It was like 1 in the morning.
Or you,
I was like,
first you ask, first you ask and get the clarification,
no.
because Richard and Gavin and I will all be there. And
So
then if that doesn't
like
work,
the
then
day
you
of ECU,
you make an assumption and
we're in
go
the
with it.
last section. I was like, good job.
Because the worst thing on these final exams is to see people who
Another
take
episode.
a hit of 0 on an entire problem, or almost the whole problem, right? I mean, that's how people fail, of course.
Threw it away.
So, the best thing is to, relax,
Was that last part?
the 3 of the problem, okay, I just finished setting the test last night, okay? So the structure is I tried to put the easier ones up front, so it'll get progressively more difficult as you go along, okay? So you can warm up. So 1 and 2, I think, okay, I've been wrong in the past, but that one with the sphere just threw me off. People couldn't handle a sphere when I did it in 2012, I think it was. So I put it up front, or third or something like that. Anyway, so the first 2, at least in my biased view, are not bad. Okay, third one's maybe slightly non-standard, and then the 4th one is the Newton-Raphson, and then the 5th one is the one that's going to maybe require some decent amount of thinking.
It's another to get touched.
So get a good night's sleep. Don't
Oh, God.
don't
Time
come
for
in
that.
Is there lots of
fatigued.
time?
I'm meeting. I haven't met with TAs. TAs are going through it now. So so I won't know till tomorrow whether, how the timing is.
They'll just come
So
back.
what I've done in the past, sometimes if it's too long, I either take a chunk or I'll make it a bonus.
Why would you do that? Yeah.
So I've done that in the past.
Bonus marks on an exam?
Yeah, so that may occur.
That never happens. Well,
Yeah.
You talked about in class that you weren't sure if you were gonna give us tell us which correlation to use or what you got to us, are you?
Okay, let me think about that for a second. No, I don't think I haven't put on the test, use such and such correlation. Okay, I have put advice, subtle advice, or not subtle, maybe not, hopefully not subtle. I put advice on when you select your correlation, keep this in mind. Okay, I can't say anything more than that, but I haven't said a specific correlation, no. And I've given most of the properties. I think I'm not sure, I think I gave all the properties that you need. So I don't think there's any property lookups.
what day is it? Tuesday?
I'm not 100% sure about that, but I'm pretty sure I gave most of the properties. Yeah. I'm trying to anyway. I don't want to waste people's time looking up properties, right? You'll need that time for
For all the fun.
all the fun stuff. Yes. Just don't panic, right?
Saw this review session did it.
Yeah.
Any of that derivation you went over today that we should focus
So-
on or
so-
brush up on?
Well, I mentioned that because to say that there are integrals and derivatives that you need to know, right, for the course. So I can say they're not going to get you to derive a thin equation, but you know that kind of thing where you got to do energy balances and come up with something that goes back to say maybe a basic equation.
Okay.
So that's the thing. Okay, why do I do that? Because I want to know whether the person understands, you know, the final equation. Say, take the fins as an example. I can't give another example without saying too much. The question is, does the person understand what is the fin? What's all the assumptions involved in the fin equation? You know, it's constant age, it's constant cross-sectional area, it's constant K, it's all those things. Okay, so if you change one of those things, what do you have to do? You got to go back to the original equation and say, what is the piece that's different now, and how do I do the right integration or differentiation or whatever to get what I need for this problem?
Okay.
So if you're sitting there saying, I don't know what he's asking me about deriving something, for sure you should ask, right? And I can say, here's what you're faced with, right? You have this situation, and here's the boundary condition, and you know this is what I'm expecting you to do.
Okay.
But even the last one, I've tried to split it into stuff that you can do, and leave sort of the stuff that's more challenging right to the very end. So I'll have to see what timing of the TAs, but and I haven't set the mark distribution yet. But I'm guessing, okay, I'm guessing that 75% of the test will be quite doable. So in questions 4, and that's excluding Newton-Raphson. Well, what's happened in the past is sometimes people can't even derive the Newton-Raphson equation. Okay, that's what happens. So if you discount that, and you discount the sort of the harder part of the last question, I think that only amounts to 25–30% of the exam.
Okay.
So there's prep work. You know, there's prep work in each of the last questions to get to the harder part.
Mhm.
Prep work should be done. So, you know, and again, I could be totally wrong, but because the way I do it is, you know, people who are, you know, they know their stuff and they stay calm and they're working through it. In 3 hours, you got to be able to do 75% of the exam like perfectly. That's in my view. If people start making some mistakes, or they just, you know, I've seen people just sort of forget stuff in exams. You know, like,
Oh yeah, I've done that.
I've done it myself. You know, you blank.
Yeah.
But so people can stay collected, and I think 3 hours is lots of time for the whole thing, but it's certainly lots of time to do 75% of the exam. So the other two things exist. What do they exist for? They exist for the people who want the A+ or the A. Right? That's why they're there. And they're not impossible at all. You know, well, unless the TAs tell me they're impossible, then I would have to adjust something.
Yeah.
But I mean, if you look at old final exams, like that one with the fin that we talked about at great length, it's a debatable, I guess, whether having to get the fin equation and apply, you know, the Q on both ends, the Q base and QL, and solve for coefficients, is that impossible? It's not mathematically impossible, but it does take a lot of thinking to say, how do I, that's what's going to happen, is people have to sit there and say, how do I use what I know to get what he's asking me to do? You know? So that was the problem with that fin equation. People couldn't figure out that they had to say minus k dt dx at x equals L is equal to QL. They couldn't figure that out. And then if you can't figure that out, you can't solve that problem. That's the reality of it. So that may occur. That may occur on Thursday. That might be you get to the last bits and you can't figure out how to proceed. So you ask your question, you know, you go back to basics, you know, you figure out what you're being asked. And I can't, so then I can't do anything after that. You know, I'm just hoping that people can see their way through to do that, but if they can't, then, I mean, it exists there, so if people can do it, I mean, I can't mince words. If people can do it, they get the A+. If they can't do it, then they get a, you know, A or B+ or B or whatever it happens to be. Just, you know, whether people agree with me or not, I mean, that's my view of what a grade in a course should mean. You know, the people who can take stuff and extend it really deeply understand the material, and they can see, you know, they can think how to rearrange things or how to make their way through something they've never seen before. Right? It's a total challenge because it's not an end of chapter problems. You haven't seen it before. So you know, that's my view anyway. And that's why people should not be fatigued. Like, I've seen people that I've seen do really well on the term, and they come to a problem like that in the exam and they just crumble because they're not thinking straight, or, you know, the stuff that they, after the test they say, oh, I knew that. You know, I knew how to do that. Or you can't see clearly. Like in the tests, there's always, you know, the combination of, you know, different chapters, right? Like we had in term tests. So I have people in the exam afterwards saying, I couldn't even figure out what chapter that was from. Right? And I don't know whether that's the person just sort of totally not thinking straight, they didn't study the stuff at all, I have no idea. But your best shot is to be, you know, on your game, right? You're not tired, and you can think clearly, and you can get the clues from the problem statement.
Yeah.
So, and then have your own strategy, right? You know, you got to find your way. Is it transient? Is it steady state? Is it cylindrical? Is it plane geometry? Is it internal convection? Is it external convection? Is it natural convection? Well, I'll be really, really, honestly, super disappointed if people don't see the quiescent and the G and don't do natural convection. I mean, really, I'll just, you know, I'll be really unhappy.
Just write them off. Just tears on the exam paper.
Yeah. So please don't do that.
Don't miss it.
What you do with it, I can't guarantee, but I mean, at least it'll be on the right path, right? Yeah, so look for clues like that. The heat exchanger one, you know, if people have studied it and they know how to use the NTU and Epsilon equations, they know how to calculate an overall U. You know, the way I would view those is those are you know, you're all geared up. You do those first. You knock them off quickly, and that gives you some breather time for the ones that you get to the end where you got to really sit and think, and maybe it takes you 15, 20 minutes to figure out what you have to do. It's the, you know, and I can't. It's the ones that I find disappointing is the people who don't do even the heat exchanger problem correctly. Yeah, that's, you know.
Should be, give me.
So my hope is that everybody here at least will, you know, just knock off the heat exchanger one without any problem. You know, knock off, you know, whatever one or the other one of the first or second problems, and you know, and then the last three will be a little bit more challenging, but one of them you've seen before, or it's been used on other final exams or term tests, so it's not something totally new. The Newton-Raphson is totally new.
Oh, yeah.
So I haven't done anything similar in the past, so that one is totally new. And the last one is totally new. So there's two where you'll be sitting there saying, okay, I haven't seen this before, but what do I do? You know, you'll have to figure out how do you make your way through it. And it's the same when people did the fin problem there, right? They'd never seen a derivation like that for the fin problem, I don't think. And they had to say, what do I do? How do I go back to something basic? Or what's my energy balance? And just enjoy the moment.
It's gonna be a long 3 hours. One more.
Or more. How many new questions a year do you think you come up with?
This year it was only the 2, 4, and, well, okay. So most of them, the ones that I categorize as the first 3, they're like modified end of chapter problems, old term test problems, old final, you know. And the same thing with the term test, you know, that platinum wire thing, I've used that lots of times.
Yeah.
No, I spent a giant amount of time on this test to do 4 and 5 because they're new. Because I had an idea, right? I got an idea and said, okay, this would be really cool to do.
Oh God. That's trouble.
And so then it's you know, a process of, so I work on it for a while, then I do the second year thermal final exam, and I come back and work on it again, and so they've just come together yesterday, just the whole thing. And I probably spent 4 or 5 days putting the final exam together. But that includes, you know, say for the first 3, includes changing the numbers so that things work out nice and round numbers, you know, like, and even I'll give you values, you know, sometimes I give values that you need right on the diagram, so first 3 are kind of optimized.
Okay.
So that, you know, so there's no giant stumbling blocks, you know, you
Yeah.
still have to know the material.
Right.
But there's no giant, you know, it's all giving properties and all that stuff to enable you to show what you know in a reasonable way. And then the last ones, there's portions that can be done, portions of each one can be done just straight up.
Yeah.
And then there's the, you know, the extender bits, which was, took a while to formulate. But I mean, it's all obviously material from the course.
Yeah.
It's just, now I don't know without saying too much, any of those types of problems, okay, let's say, not the fin one, that chapter 8 one where I did the internal flow, it was the one, problem 851.
Okay.
And it has a helium in a tube from a reactor or something. Anyway, I managed to get a Newton-Raphson equation from that, okay? And it really, all it was, in that instance, was writing 3 equations. You know, like the TS equation
Right. Yeah.
for, you know, for tube, Reynolds number equation, and maybe a Nusselt equation, right? It's the 3 equations that go together, and they're all nonlinear, and it was just knitting those equations together correctly to get an F of t equation. Okay, so that's essentially what is going to happen on Thursday. Is there's a set of, you know, equations you have to put together and derive a nonlinear equation from.
Yeah, I think you did that for your 2009 Newton-Raphson question.
Yeah, so I don't know. Nope. 2009. Where did it go?
Up there.
That's your, I think it's the last question. Yeah, question 5.
Yeah, so that's what I'm talking about. That's the one I was talking about. So this one.
Here's the Newton-Raphson.
This one was 5.
He gave it.
So this one you had a number of equations, okay? A number of equations. So so this is what I'm saying. It's somebody who knows how to analyze a problem and say, okay, what do I know? What don't I know? What equations are pertinent? You know, what quantities do I know? Do I know TS? Do I know TMO? Do I know TMI? So you're sort of surveying the governing equations or the algebraic equations that work for your problem. So this one, you had to say, take this equation and this equation and this equation and say, how do I knit those all together to get some? So you're looking for one unknown. I don't know what the unknown was.
I think you're looking for TS, but you have to put everything in terms of your mass flow rate.
What was the F of t equation? Oh, it's here. Sorry, it's here. So you're repeating. So there's a prime example. The first part was doable. It was sort of the warm-up with the, you know, using the analysis. And then the second part is you have to recognize that you have to put a bunch of equations together and extract out, extract out quantities. Like if you're looking for m dot, you're going to extract it out algebraically from some equation and combine it with something else. And so that's in terms of m dot. So, well, yeah, TMO. Okay. So you got to say, okay. So how do you do that? I'm going to say which equation, what thing you're solving for, right? So in this case, I said solve for TMO. So if you want to work backwards, you look at all your equations that apply and say, where does TMO appear in those equations? Or how can I gather those equations together, to get TMO in here by itself, all with constants? So this one was not easy. I would not call that easy. You had to, so this is the stumbling block, okay? So this is where somebody comes to these, and if you can see your way through to get those three equations, probably you're okay. If you can't get started in those three equations, maybe you're not okay. That's the way it is. So that's the difficulty with giving a problem like this, is people could say, he didn't give me a chance to show what I know, because if I had this equation, I could do the derivative, I could do the Newton-Raphson iterations and all that sort of stuff. So I can see that. That's the frustrating part of that kind of a question. Because if you can't get the f of t, you can't get the f prime of t, you can't do the iteration.
But the majority of the marks would be deriving those equations anyways, not performing the Newton-Raphson.
That's right. Exactly. Yeah. Yeah, still to be determined, but that's generally what I do.
Yeah.
Even the derivative is not worth a giant amount of marks,
Yeah.
because it's just simple or whatever derivative. Yeah, so it's the thought process of what equations do I need. So if you're getting stuck on this, for example, sit and say, okay, what equations do I have available to me? And you might pick one up, or you could write them all down and start analyzing them, and you can cross one off if you want and say, no, that doesn't like that applies, and dig something else out. So I just want to, okay, so if I'm talking now about it, I want to scare people to some degree so they prepare well, hoping that when you get to see it, they'll say, oh, I can see that. That's not so hard after all.
Mm-hmm.
But I did do, the thing that I like about this here one is that it's not, it's more like this style compared to the ones which are just temperature. So, it's it's radiation plus natural convection or something like whatever I did in 2012. It's more putting a few equations together and a quantity that you wouldn't normally solve. I honestly think you'll like it. But what it does, it requires the entrance fee is getting over the hurdle of understanding what it is that I'm asking you. So again, ask, I don't mind if I go around to 70 people and explain the same thing again. It doesn't bother me a bit. And Gavin and Richard will know the same thing. They're going through it right now. How we doing? Okay.
Time was for good.
Nothing more? I can stay and, so what I did, I've done these before. When we run out of steam here, usually I just sort of hang around, people come and ask questions or circulate and ask questions. So unless there's another particular final exam question you want to go over, then maybe we'll, or there's other questions of a general nature, I can just hang around. Please come and check the files here. I don't like to keep people's old assignments and term tests and things, so if you have a look here, maybe there's something, see a couple.
Oh, hey, look at that. Missed one.
There's one here unclaimed.
Oh, I think that about does